You know, every time a plane takes off, it's doing more than just defying gravity. It's in a constant negotiation with a whole host of invisible forces. We're talking temperature, air pressure, wind, you name it. And pilots, they manage this incredibly complex dance using a kind of playbook, a set of rules and calculations that are absolutely critical for a safe flight. So how on earth do they do it? Well, to get us started, let me ask you a question. Just picture a cockpit for a second, right? All those dials and screens. What do you think is the single most important instrument for a safe takeoff? Maybe the airspeed indicator, the engine gauges? What do you think? The answer? Well, it might actually surprise you because on a hot day at a high-altitude airport, one of the most critical instruments in that entire cockpit is just a simple thermometer. And understanding why that is, well, that's the key to the very first chapter of the pilot's performance playbook. And that's because a plane's ability to fly, its raw power, its lift, everything, is profoundly affected by the air it's moving through. And that air, well, it's always playing some hidden tricks on the machine. Okay, so the first thing we gotta wrap our heads around is something called pressure altitude. The easiest way to think about it is that it creates a level playing field for every pilot everywhere. Since air pressure is always changing with the weather, pressure altitude gives pilots a standard baseline to work from. It's really step one in figuring out how the airplane is actually going to perform on any given day. All right, now for the really crucial one, density altitude. What we do here is take that pressure altitude and then we correct it for temperature. See, hot air is way less dense than cold air, and this is where that simple thermometer suddenly becomes so important. Pilots often call density altitude the performance altitude, and for good reason. It's what tells them how the plane is truly going to perform. And this, right here, is the key idea. Density altitude is the altitude the airplane feels like it's at. So you could be sitting at an airport that's 5,000 feet above sea level, but on a really hot day, the air is so thin that your plane will perform as if it's taking off from 8,000 feet, or maybe even higher. That's a huge difference. So what does this thin air actually do to the plane? Well, it hurts performance in three major ways. First, the engine gets less air, so it can't produce as much power. Second, the propeller has less air to bite into, so it generates less thrust. And finally, the wings have fewer air molecules to push against, meaning they create less lift. So you've got less power, less thrust, and less lift. That is a really dangerous combination. Okay, so knowing all this, how does a pilot actually put it all together? That brings us to the next phase, the super important calculations that have to happen long before the plane even thinks about starting to roll. Let's put ourselves in the cockpit for a second. Imagine you're at a high-elevation airport. It's a hot afternoon, and the air is thin. How do you know for a fact that the runway in front of you is long enough to get airborne safely? You don't guess, you calculate. Pilots use these performance charts that factor in all of these different variables. Of course, a higher weight is a huge one. It means you need more speed and a longer takeoff roll. We've already talked about density altitude. But things like wind and even the slope of the runway are just as critical. A headwind is a pilot's best friend on takeoff. It seriously reduces the amount of runway you need. But a tailwind, even a tiny one, is incredibly dangerous and can dramatically increase the distance you need to get into the air.
And just look at this. It shows you how much of a difference that wind makes. A measly 10-knot headwind can shorten your takeoff distance by almost 20%. But flip that around, and a 10-knot tailwind, the same exact speed, just in the opposite direction, can increase your required distance by over 20%. That is a massive swing from what seems like a pretty small factor.
Okay, so you've done your homework, you've calculated your takeoff, and you're safely in the air. Awesome. The next challenge is getting to your cruising altitude efficiently and safely. And here again, pilots have specific strategies right out of the playbook. You know, climbing isn't just about pulling back on the stick. Pilots use two totally different methods depending on what they need to do. If you have to clear some tall trees at the end of a really short runway, you use something called VX, or best angle of climb. It gives you the most altitude gain over the shortest horizontal distance. But if you're clear of obstacles and you just want to get up high, you use VY, the best rate of climb. That gets you to your cruising altitude in the shortest amount of time. Two different tools for two very different jobs. So what goes up must come down, right? And the art of landing, well, it introduces its own unique set of physical puzzles. It is not just a takeoff in reverse. In some ways, the physics involved are even more challenging. So here's another one for you. And this one sounds like a total riddle.
When does a pilot actually need to add more power just to fly slower while staying at the same altitude? It sounds completely backwards.
Well, the answer is this crazy-sounding thing called the region of reverse command. It's this counterintuitive state you get into on a landing approach. At these really low speeds, the airplane's drag just increases dramatically. So to fly slower without dropping out of the sky, you actually need more power, not less. It is an absolutely critical concept pilots have to master to avoid a bad situation close to the ground. And believe it or not, the challenges don't end when the wheels touch down. If the runway's wet, you've got the very real danger of hydroplaning. This is where a layer of water builds up between the tires and the pavement, and it basically turns your airplane into a boat with no rudder and, even worse, no brakes. So how do pilots know when this might happen? Well, they can actually estimate the speed where hydroplaning becomes a real risk with a surprisingly simple formula. You just take the square root of the main tire pressure and you multiply it by 9. That's it. So what does that mean? Well, for a small plane with a tire pressure of, say, 36 psi, that means the plane can start hydroplaning at just 54 knots. That one number tells the pilot exactly how slow they need to get before their brakes will even have a chance of working again. So when you put it all together, from takeoff to landing, flying is this constant process of calculation, of anticipation, and just having a healthy respect for all those invisible forces in the atmosphere. It all comes back to that pilot's performance playbook. And look, don't just take my word for it. This is a direct quote from an official aircraft flight manual. It basically says that all the charts and data in the world are completely useless unless the pilot understands all these variables we've been talking about and knows how to adjust for them. This isn't optional knowledge. It's the absolute foundation of flying safe. So in the end, it all comes down to this. Every single pilot is constantly running a mental checklist of these invisible forces. They're always assessing the plane's weight, the altitude, the temperature, the wind, and the runway itself. This is the playbook in action on every single flight. So the next time you see an airplane accelerating down a runway, just remember that invisible dance that's taking place. It's not just a show of raw power. It's the successful end of a whole series of complex calculations. A careful, quiet negotiation between the machine, the pilot's playbook, and the hidden tricks of the air.